Hello, welcome. In this section, we will begin our study of solution methods with the simplest of all differential equations. This and many other methods we will discuss in this course involve integration. So it is useful to refresh our memory on important formulas and techniques such as integration by parts by consulting a calculus text. Let's begin our discussion with a spatial form of differential equation. A first-order ordinary differential equation of this form is called separable if the function f can be factored into a function of x and a function of y only. That is, if f of x comma y can be written as a product of two functions, g of function of x only and h function of y only. For example, the equation y prime equals 2xy is separable. Here, f of xy equals 2 times x times y and g of x equals 2x and h of y equals y. We might also consider g of x equals x and h of y equals 2y. However, the equation y prime equals x plus y is not separable because the right-hand side cannot be written as a product of two functions, one of which the function of x only and the other one is a function of y only. Method of solution. Consider the following separable equation. Y prime equals g of x times h of y. By letting h of y not equal 0 and dividing both sides by h of y, we obtain 1 over h of y times y prime equals g of x. We just transposed this term h of y to the left hand side as 1 over h of y. Now we consider 1 over h of y is some function k of y. So the left hand side becomes k of y times y prime equals g of x. Suppose there exists a function h of y such that h prime of y equals k of y. Then the left hand side of equation 4.1.2 can be written as h prime of y times y prime equals g of x. Now the left hand side of equation 4.1.3 can be put into the following form by using the chain rule of differentiation. Now, integrating both sides with respect to x, we find h of y in the left hand side equals the integral of g of x plus an arbitrary constant, or h of y equals g of x plus c, where this g, capital G, is simply the integral of the small c. The equation 4.1.3 here is the general solution of equation 4.1.1. Let's have a look at an example. We want to solve the differential equation y prime equals 2 times xy. And we'll also define the interval of definition of the solution. Before we divide the equation by y, we note that y of x equals 0 is a constant solution of the given equation on the interval from negative infinity to positive infinity. Now, to find the non-constant solutions, we divide the equation by y and obtain 1 over y times y prime equals 2x. Now, the left-hand side of this equation can be put as the derivative of the quantity natural log of absolute value of y. Recall the formula that the derivative of the natural log of absolute value of y with respect to x is equal to 1 over y times the derivative of y with respect to x. Here, prime denotes the differentiation with respect to x. This is the chain rule. Now, integrating both sides with respect to x, we obtain in the left-hand side the natural log of the absolute value of y, and in the right-hand side, we obtain x squared plus an arbitrary constant c. This equation is a solution of the differential equation we were given, namely y prime equals 2x times y. This is called an implicit solution. In this case, we can express y in terms of x only, which would be called the explicit solution. In order to find that, we exponentiate both sides of this equation and get absolute value of y in the left-hand side, and in the right-hand side we get e to the x squared plus c. But this term here can be written as a product of two exponentials, e to the c times e to the x squared, as shown here. Now, if we remove the absolute value bars from the left-hand side, we must put a plus or minus symbol to the right-hand side. And this gives this step. Therefore, y equals c1 times e to the x squared, where c1 equals plus or minus e to the c. Since e to the c is strictly positive, we have c1 not equal 0. It can be either positive if we choose the positive symbol. It can be negative if we choose the negative sign. Now we can put all the constant and non-constant solutions into a single expression as follows. Y equals k times e to the x squared, which gives the general solution of the differential equation y prime equals 2xy. If k equals 0, we recover the constant solution, namely y of x equals 0. And if k is not equal 0, we recover the non-constant solutions as defined in equation 4.1.1.2. Now we observe that since we defined h by h prime of y equals k of y, then h of y is an antiderivative of the function k. This observation suggests an alternative method for solving equations like this by using the differentials dx and dy. Since we had k of y times y primes equal g of x, but recall y prime is the ratio of the differentials. In other words, the derivative of y with respect to x, written dy by dx. So if we transpose the term dx to the right hand side, we obtained an equation like this. This is called a differential form, in which the variables are separated. Now, integrating the left hand and right hand sides with respect to y and x respectively, we also obtain the same solution. For example, the non-constant solutions of example 4.1.1 can also be obtained as follows. We had y prime equals 2xy. Then for the non-constant solution, we can divide the equation by y. We obtain dy by y equals 2x times dx after separating the differentials. And then integrating both sides, we obtain equation 4.1.4 as discussed previously, which can be put into the following explicit form as shown previously: y equals ax squared. An important note: in equation 4.1.4, we do not need to put two arbitrary constants, for example c1 and c2, in the both sides as the natural log of absolute value of y plus c1 in the left hand side when we integrate it equals x squared plus c2 in the right hand side when we integrate it, because these constants can ultimately be incorporated into a single constant c as follows. Let's consider another example. We need to solve the following initial value problem. Y prime equals x over 2y with the initial condition y at 2 equals 1. The given equation can be written in this form: 2y times y prime equals x, just by moving the term 2y from the right hand side in the denominator to the left hand side as a factor of y prime. And then the left hand side can be written by the chain rule as a derivative of the term y squared with respect to x. Because if we differentiate y squared with respect to x, we would obtain 2y times y prime, which is equals to x, the same right hand side. Now integrating both sides with respect to x, we obtain y squared in the left hand side, and in the right hand side x squared over 2 plus the arbitrary constant c, which can be reorganized as the following equation shown in the box. Now, to obtain the particular solution, we need to apply the initial value condition, which is shown here. So we apply this condition to the equation, and which gives us the c value -1, which when substituted to the equation in this box gives the equation shown in the box below. This is the particular solution of the differential equation. Y prime equals x over 2y with the initial condition that y at 2 equals 1. Alternatively, the solution of the previous equation, y prime equals x over 2y can be obtained by writing the equation in terms of differentials. So the ODE written in terms of differentials would take this form. Now integrating both sides, we would obtain y squared in the left hand side and x squared over 2 plus c in the right hand side. And c is the arbitrary constant. Now the initial condition, y at 2 equals 1, gives the c value -1, which when substituted to the equation gives us the equation shown in the box.